A JK flip-flop is a bistable circuit that stores one bit of information. It has two inputs, J and K, and a clock, CLK. The characteristic equation tells us what the next state, Q plus, will be for any combination of present state, Q, and inputs. Q plus equals J times not Q plus not K times Q. If J equals 0 and K equals 0, the term J times not Q is 0 and not K times Q equals Q, so Q plus equals Q, no change. If J equals 0 and K equals 1, the second term becomes 0, so Q plus equals 0, reset. If J equals 1 and K equals 0, the first term becomes not Q, so Q plus equals 1, set. If J equals 1 and K equals 1, both terms reduce to not Q plus Q equals 1, which simplifies to Q plus equals not Q, toggle. The truth table simply lists these four cases together with the clock edge, normally the rising edge. J0, K0, QT0, QT plus 0, no change. J0, K0, QT1, QT plus 1, no change. J0, K1, X0, reset. J1, K0, X1, set. J1, K1, 0, 1, toggle. J1, K1, 1, 0, toggle. Think of the JK flip-flop like a light switch with two buttons, one that forces the light on, J, one that forces it off, K, and when both are pressed together the light simply flips its current state. The clock is the moment you press the apply button. The switch only looks at J and K at that instant. An excitation table is the reverse of the characteristic table. Instead of asking given J and K, what is the next state, we ask what J and K values are needed to move from a present state Q to a required next state Q plus. This is useful when designing state machines because we often know the desired state sequence and must derive the control inputs. X means don't care, any value will satisfy the transition. For example, to move from 0 to 1 we must set J equals 1 for set, while K can be either 0 or 1 because the K input is ignored when J equals 1. State transition analysis uses the excitation table together with a state diagram. Imagine a simple 2-bit binary counter built from two JK flip-flops. Q1 equals MSB. Q0 equals LSB. The desired sequence is 00 to 01 to 10 to 11 to 00. By writing the present state / next state pairs for each flip-flop and consulting the excitation table, we obtain the required J and K inputs for each clock cycle. This systematic approach prevents missing a required toggle condition and makes the design scalable to many states. A real-world analogy. Think of a railway yard where a train, the bit, must move from one track state to another. The signal lights J and K tell the driver whether to stay, move forward, reverse, or switch direction. The excitation table is the rule book that tells the signal operator which lights to turn on to achieve the required movement. A synchronous counter changes all its flip-flops on the same clock edge, unlike asynchronous ripple counters, where each flip-flop is triggered by the previous one. JK flip-flops are ideal for synchronous counters because the toggle condition J equals K equals 1 can be generated easily with simple combinational logic. Step 1. Determine the counting sequence. For a binary up counter, the sequence is 000, 001, 010, 011, 100, and so on. Step 2. Write the present state next state table for each flip-flop. For a 3-bit counter, the rows look like Q2, Q1, Q0 leads to Q2 plus Q1 plus Q0 plus. Step 3. Create excitation tables for each flip-flop using the present state next state pairs. For the least significant bit Q0, the transition is always 0 to 1 or 1 to 0, so J0 equals K0 equals 1, always toggle. For the next bit Q1, the toggle occurs only when Q0 equals 1, i.e. on every second clock, thus J1 equals K1 equals Q0. For Q2, J2 equals K2 equals Q0, and Q1, logical AND, toggle every fourth clock. Step 4. Implement the logic. AND gates generate the required product terms, for example Q0 and Q1 for the most significant bit. The J and K inputs of each JK flip-flop are tied together J equals K because we only need the toggle mode. Step 5. Add a common clock. All flip-flops receive the same clock edge, making the counter synchronous. Why JK? If we used a D flip-flop, we would need extra logic to compute D equals Q exclusive OR toggle condition. With JK, the toggle condition is native, simply drive J and K high when we want to toggle. Real-world example, consider a digital watch that counts seconds. Its seconds counter uses a synchronous binary counter so that all bits change together at the exact moment a new second begins. This avoids glitches that would show an incorrect intermediate number on the display. Mathematically, the next state function for bit I in an n-bit up counter is ji equals ki equals the product from k equals 0 to I minus 1 of qk, which is the logical AND of all lower order bits. If any lower bit is 0, the product is 0, and the higher bit holds its value only when all lower bits are 1 does the higher bit toggle. The race around condition happens in a level-triggered JK flip-flop, when the clock pulse is longer than the time it takes for a change to propagate through the device. Imagine the clock as a gate that stays open for a period TCLK. When J equals K equals 1, the flip-flop wants to toggle. As soon as the first toggle occurs, the new output feeds back to the inputs because J and K are both tied to the output in the toggle mode. If the clock is still high, this new output can cause a second toggle and then a third and so on, racing around the internal feedback loop until the clock finally goes low. Mathematical criterions. TPD equals internal propagation delay time from clock edge to output change. If the clock pulse width TCLK satisfies TCLK less than 2 times TPD, the output will have time to toggle only once before the clock closes, preventing the race around. If TCLK is larger, the output may toggle more than once, leading to an incorrect final state. Effects. The flip-flop can end up in an unpredictable state, often the original state, effectively canceling the toggle. In counters, a race around can cause missed counts or double counts, which is disastrous for timing critical systems such as digital clocks or communication protocols. Analogy. Think of a revolving door that you open with a button in the clock. If you keep the button pressed too long, the door may spin multiple times before you let go, and you cannot guarantee whether you end up inside or outside. A short press guarantees exactly 1 rotation. Designers avoid race around by making the clock pulse narrow, using master-slave arrangements, or employing edge-triggered flip-flops that only react to a momentary edge rather than the whole level. A master-slave JK flip-flop breaks the level-triggered operation into 2 stages, so that the feedback loop cannot race while the clock is high. The circuit consists of 2 JK latches. Master latch is transparent, passes inputs to its internal node when the clock is high. Slave latch is transparent when the clock is low. During the high phase, the master records the J and K values, but its output is held internally. When the clock goes low, the master stops changing and the slave becomes transparent, copying the master's stored value to the final Q output. Because the slave only sees the master's stable output after the clock edge, the internal feedback which would cause race around is broken. The slave cannot toggle until the clock has transitioned low, and the master cannot change while the slave is active. This effectively makes the flip-flop edge triggered. The state changes once on the falling or rising edge, depending on design, regardless of how long the clock level lasts. Why it eliminates race around. The feedback path exists only inside the master latch, which is disabled when the slave is active. The slave sees a static value, so no additional toggles can be generated until the next clock edge. Real-world picture. Imagine a 2-person relay race where the first runner, master, runs while the baton is handed, but the second runner, slave, only starts running after the first runner passes a finish line clock transition. No matter how long the first runner runs, the second runner cannot start early, preventing a race that would cause confusion. Mathematically, the master-slave flip-flop's characteristic equation is the same as the JK/S, but the timing ensures the output updates only on the clock edge, satisfying the race around avoidance condition without needing to limit T-clock. Even with a master-slave design, timing constraints are still crucial. The key parameters for an edge-triggered JK flip-flop are: setup time T-setup dash the minimum time the J and K inputs must be stable before the active clock edge. If the inputs change later than this, the flip-flop may capture the wrong value. Mathematically, T-setup less than or equal to arrival time of input minus clock edge time. Hold time T-hold dash the minimum time the inputs must remain stable after the clock edge. Violating this can cause the flip-flop to read a transient value. Mathematically, T-hold less than or equal to clock edge time minus departure time of input. Clock to Q propagation delay, TCQ or T clock to Q, dash the time taken for the output Q to reflect the new state after a valid clock edge. This delay determines the maximum operating frequency of a sequential circuit. For a chain of flip-flops, the clock period must satisfy T clock greater than or equal to TCQ max plus T logic max plus T setup, where T logic max is the worst-case combinational delay between flip-flops. Practical analogy, consider a school bell clock that signals the start of a class. The teacher flip-flop must receive the lesson plan JK a little before the bell rings set up and keep it unchanged until the bell rings hold. After the bell, it takes a few seconds clock to Q for the teacher to start teaching output changes. If any of these times are violated, the system behaves unpredictably, just as a teacher who hears the bell after changing the lesson plan mid-class would confuse the students. Problem 1 - toggle frequency. A JK flip-flop has a clock to Q delay TCQ equals 8 nanoseconds, and the combinational logic feeding its J and K inputs has a maximum delay of 5 nanoseconds. The flip-flop is used as a free-running toggle J equals K equals 1. What is the maximum toggle frequency? A solution. The clock period must satisfy T clock greater than or equal to TCQ plus T logic plus T setup. Assuming a typical T setup of 2 nanoseconds. T clock greater than or equal to 8 nanoseconds plus 5 nanoseconds plus 2 nanoseconds equals 15 nanoseconds. Maximum frequency equals 1 divided by 15 nanoseconds, approximately 66.7 MHz. Problem 2 - propagation delay in a 4-bit synchronous counter. Each JK flip-flop has TCQ equals 6 nanoseconds. The AND gates that generate the toggle condition for the most significant bit have a delay of 3 nanoseconds. Determine the minimum clock period for reliable operation. A solution. The worst-case path is through 3 AND gates for Q0, Q1, Q2 plus the flip-flop delay. T clock greater than or equal to T logic max plus TCQ plus T setup equals 3 times 3 nanoseconds plus 6 nanoseconds plus 2 nanoseconds equals 17 nanoseconds. Thus, the counter can run up to approximately 58.8 MHz. Problem 3 - race around prevention. A level-triggered JK flip-flop has an internal propagation delay TPD equals 4 nanoseconds. What is the maximum allowable clock pulse width to avoid race around? A solution. Using the criterion T clock less than 2 times TPD. T clock max equals 2 times TPD equals 8 nanoseconds. Any clock pulse longer than 8 nanoseconds may cause the output to toggle more than once. Designers therefore either narrow the clock or use a master-slave configuration. These examples show how timing numbers translate directly into design decisions such as clock frequency limits and whether extra circuitry master-slave is needed. Write the characteristic equation of a JK flip-flop and explain each term. Pitfall: forgetting the complement on K, i.e. writing J, and Q plus K bar Q, which actually describes an SR flip-flop. The correct JK equation is Q plus equals J bar Q plus bar KQ. Given the present state 101, what J and K inputs are required for the next state 110? Pitfall: not using the excitation table. Students sometimes assume J equals K equals 1 for any change the proper method. For Q2, most significant bit 1 to 1 J2 equals 0, K2 equals X hold. For Q1 0 to 1 J1 equals 1, K1 equals X set. For Q0 1 to 0 J0 equals X, K0 equals 1 reset. Determine the maximum clock frequency for a synchronous 3-bit counter where each flip-flop has TCQ equals 5 nanoseconds and each AND gate has TG equals 2 nanoseconds. Pitfall: ignoring the combinational delay of the most significant bits and gate which has 3 inputs. The worst-case delay equals 3 times 2 nanoseconds equals 6 nanoseconds, so T clock greater than or equal to 5 nanoseconds plus 6 nanoseconds plus T setup approximately 2 nanoseconds equals 13 nanoseconds, therefore F max approximately 77 MHz. Explain the race around condition and state the inequality that must be satisfied to avoid it. Pitfall: mentioning only clock must be short without giving the quantitative rule. The correct inequality is T clock less than 2 times TPD or equivalently T clock divided by 2 less than TPD. Why does a master-slave JK flip-flop eliminate race around? Pitfall answering merely because it has two stages. The deeper answer, the master samples inputs. While the clock is high, the slave updates the output only after the clock falls, breaking the feedback loop during the active clock level and converting the device into an edge-triggered element. List the timing parameters for an edge-triggered JK flip-flop and describe how they affect the maximum operating frequency. Pitfall forgetting to include hold time or mixing up setup with hold. The full set is T setup, T hold, and T clock to Q. The clock period must satisfy T clock greater than or equal to TCQ max plus T logic max plus T setup. Common overall pitfalls: mixing up SR and JK equations. The complement on K is often mistreating the clock as a pulse when the device is actually level triggered, leading to misunderstanding of race around. Ignoring the don't care conditions X and excitation tables, which can simplify logic, but are sometimes omitted, assuming that making the clock narrower always solves race around without checking the actual propagation delay of the specific IC. When studying, always start from the truth characteristic tables, then move to excitation tables, and finally map the required logic onto timing constraints. This systematic approach prevents most mistakes on exams and in real designs.